So this is something that I've only started looking into very recently, and I should have, and I always knew this actually would be a consequence of my theory of quantum gravity. This quantum gravity theory that I've been working on for the past several years, I knew really quite early on that one of the consequences of this theory would be that antimatter doesn't exist, or that antimatter isn't what we think it is. That yeah, like Paul Dirac really said in the 1930s, there would instead be a hole in the background, and through this hole, I think a W plus particle would tunnel to be then reuptaken by the background in exchange for an emitted photon. So then you could have things like positron emission tomography, but really positron emission tomography isn't using positrons. It's just using something called a W plus particle. That's one of the gauge bosons of the Standard Model. So this really, I mean, it's kind of like cutting the Standard Model in half, really, isn't it? This approach to quantum gravity, since well, it does explain why there's so little antimatter in the universe at present, and why antimatter is so hard to generate, I think. And it does also solve the baryon asymmetry problem in the very early universe, and this problem of there being apparently so much antimatter in the early universe and not enough matter. We can just sort of get rid of antimatter and say that it's a phantasm, that it's nonsense, and we can go back to having just the ordinary particles of the Standard Model in terms of ordinary matter. But yeah, this does, I think this is the reason why there's been so little progress in the study of quantum gravity over the past 70 years or so. I think it makes a lot of sense that someone outside the community of researchers would eventually have more success than people within that community, because I think within that community, you know, you've got these Nobel Prizes, right? You've got these godlike figures like Paul Dirac held aloft, and ideas like antimatter just could never be questioned. You know, it's like questioning a fundamental element of quantum theory, or it'd be considered a fundamental element of quantum theory or quantum field theory that we have antimatter. And it's come down to us in the physics that's been written since. And I think it's been stifling and stymieing progress to some great extent. And it's, yeah, not hard to see why so few people in physics, frankly, would lack the cojones, lack the balls to question things like antimatter. You know, they might get laughed out of their fellowships or something, and, you know, not have the same success in academia if they're not singing from the same hymn sheet. And yeah, I do think even in very rigorous, fine academic sciences like physics, you can have items of dogma percolate down through generations and have outstanding problems like quantum gravity that really require very radical overhaulings of our understanding of fundamental physics indeed. So it's a tricky area in which to work, I think, even as an outsider. Well, I mean, it's a tricky area for anyone to work in because the physics is so difficult, and because now, anyway, through what I've discovered, I think, about antimatter, that so much of the physics from the past might just lead down blind alleys, and there's also that element of the problem. So it's very, very miasmic and confusing. I hopefully go the same way as miasma as well in epidemiology, and might go the same way as phlogiston in chemistry, hopefully. But bringing back actually a sort of etheric model, almost, a model where in the gravitational field, the background of space-time is basically particle-based, and where photons move in these zigzag patterns between background electrons, and that is their wavelength. And the reason why they have a wavelength at all is because electrons in the background seem to exhibit some sort of preference for higher energy particles, whereas they're less likely to absorb a radio wave because they're trying to get back to some baseline mass energy or something like this for the electron, whatever that would be. And yeah, a radio wave, for whatever reason it is less likely to be absorbed by the background again than a gamma ray, for instance. And so you have to really start overhauling physics and really start leading physics in a new direction if you want to have a functioning theory of quantum gravity, I think. And there's also there's no way of testing for the existence of antimatter as opposed to testing for the model that I put forward, if you see what I mean. There's no way to delineate between the two because they produce the same effects. So in test, you'd have to eventually start testing for my model, which I believe you can do in a number of different ways. You can, for instance, perform muon G-2 experiments in space, where I believe that the G factor of the muon would accord with the predictions of the standard model so long as it's in microgravity. Then you've got other ways. You can look at supernovae, and see the light escaping the neutrinos escaping 8 minutes before the light escapes. So you've got this cloud of electrons, falling back in with the implosion of the star. They're trapping all this light that's trying to escape because light bounces off electrons. It doesn't bounce off, neutrinos don't bounce off electrons, or the passage of neutrinos through space wouldn't be impeded by a cloud of electrons closing back in on it. So you've got these various different ways, I think, of testing for my model. Which I think I put more on the table in terms of testability, certainly than string theory, and probably more than loop quantum gravity as well, I think I tend to say. So I think my model is the most testable model out there for quantum gravity, and no one wants to entertain it. And no one wants to entertain it because we would have to start ripping up physics textbooks and saying that all this stuff from the past 80 years or so in physics is wrong. I had to really go back to basics and really go back to fundamentals with the standard model and with what we know about particles and really start questioning everything again. Well, not everything, but have to start questioning a hell of a lot that we've been taking for granted. And that's largely the reason why I think my theory has been unsuccessful so far. So thank you.